And then what is the rest of the part? How is the unorganized
you can look at static structure factor. So you can look at the static structure factor in this regime, and you know that there is no long range order that's developing.
So that's because that explains.
Yes, yes. So you can do both. Yeah.
There are some liquids which, when you supercool it,
Yes.
they also go into crystal formation much later temperature. For example.
Okay.
So they go into supercooled phase.
Yes.
Then when the time or something is detected to crystallize.
Oh yeah. So
does ethanol also belong to that class?
So I unfortunately don't know if ethanol belongs to a fragile glass former or not, but all I can say is that if you wait in this regime long enough, it's a metastable state. If you wait for a long enough duration, you are likely to see the nucleus from which you might grow. Yes.
So then you see that heat capacities in the crystal and are also matching, right?
At much lower once it hits the glass phase, yes. Once it's beyond the glass transition, in which there are no molecular relaxations going on. I don't break cages, I don't get to reconfigure, I am caught in the same minima in the landscape. That's when I fall into a glass. Yeah. Okay. So what I can do is, starting from the heat capacity, I can measure the entropy. And so this is what was done. Okay. So this is basically the entropy for the same system. Liquid, I have this jump, I get the crystal, and so this is the supercooled regime. And this jump here is basically this jump here. Okay. And I finally, so that's the dashed line. But now what I can do is, I can look at the difference in entropy between the liquid and between the metastable liquid and the crystal. And that difference is finite simply because of the number of different ways you can form a metastable liquid as opposed to one unique crystal. Okay? But then what you can do is, what was done by Kauzmann in about 1950s is the following, right? You can say that I'm going to think of an experiment in which I'm able to suppress this jump in the heat capacity by cooling it fast enough. I figure out a way to do that. And I basically keep extrapolating. So this is an extrapolation. So this is where I form the glass. This is an extrapolation, but I'm allowed to do that. Okay? And what it seems to do is, it seems to cross over the crystal line at some finite temperature. The entropy of the metastable liquid, the configurational entropy, so the difference would be the configurational entropy, seems to cross that of the crystal at some finite temperature, okay, which we call Tk after Kauzmann. Okay, Kauzmann himself didn't call it the Kauzmann temperature; he called it a kinetic spinodal, but we call it the Kauzmann temperature. All right, and the problem is, if you continue cooling it further, so that you cross the line further down, okay, at some at 0 Kelvin, you basically have finite entropy. If you were to just continue with this line, okay, and that's called as the Kauzmann paradox, because this is not allowed. Okay, so what Kauzmann basically said was that before such a crisis happens, it can be averted by the formation of an ideal glassy state. Nobody knows what this ideal glassy state is. Okay, we still don't know what it is, but it can be the fact that you have the fact that entropy is zero at finite temperature. Okay.
What is the understanding of the liquid entropy going lower than the crystal?
Oh, so there is nothing that forbids such a transition from happening. For example, if you take hard spheres, the simple case of hard sphere interactions, you know that the crystal, basically the crystallization process happens because you get to maximize vibrational entropy. So there is nothing that says configuration entropy of the liquid cannot be smaller than that of the crystal. But what happens is, if you continue the extrapolation further, that is the paradox.
So why can't entropy become zero? Configuration entropy becomes
No, so it is just, so you have to have one. Oh, so if you can't, yeah. So the initial problem is this. We know in the case of hard spheres this is allowed. So if you come further down, you basically have the entropy going to zero at a finite temperature. All right. So which means that there is something going on here. So you do agree that below 50 Kelvin, there is something going on. So which is why if we access that state by some process of cooling, it may be what you call the ideal glassy state. Okay, but we still can't access it.
But it is in the crystal phase. But it is part of the crystal phase.
No.
Still talking about the glass line.
I'm talking about this line.
In the phase diagram.
Yes.
Well, what happens?
So this is, I'm talking about this particular line. It's crossed the crystal at some point. Okay.
So there are many systems available in study.
Yes.
Is there any known experimental example, not this going to zero?
Yes.
The liquid entropy being lower than
No. So okay. I'll just come to that in a minute. I think I can address that question. Okay. Okay. So now
I'm talking about this crossing, not the extrapolation.
I know. I'll just come to that. We drop out of equilibrium way before, so we never get there. So which is why there is a huge confusion. Okay. So okay, now let's hang on to this temperature called Tk. Tk is the temperature at which the configurational entropy dies to zero. Okay. Now, and please remember T naught. T naught was the temperature in the previous slide at which the viscosity or the relaxation time diverged at a finite temperature. Okay, that's a dynamical quantity. This is a thermodynamic quantity. Okay, now see what happens when you plot T naught and Tk versus each other. This is for a whole bunch of different glass formers, and what? Yes, the bane of the glass problem is extrapolations. Okay, but then it allows you to open up so many things to do. Okay, so you see, I'm plotting Tk, which is where the configurational entropy goes down to zero, versus T naught, which is where the viscosity of the relaxation time diverges. It's beautifully linear. Okay, so people think there is a relationship between the vanishing of the configurational entropy and it's related to the growth of relaxation times, which is purely a thermodynamic phenomenon. Okay, now the main question in the glass problem is dynamics slave to thermodynamics. Okay, and I won't go into this paper, but it tells you that if you have a divergence at a finite temperature, if relaxation times diverge at a finite temperature, you have to be accompanied by a growing static length scale. That is an explicit mathematical proof that these people have put up. I don't understand the paper, but that's all I want to claim about this. Okay, so it basically tells you there is some sort of so this is why there is a fight between the kinetic community, which also extrapolates to T equal to 0, and the thermodynamic community, which has to do two extrapolations. Okay, and now I told you that you can go around and measure all the relaxation times in whichever manner you want, and you can't tell the difference. By accessing relaxation time data, you will never be able to tell, because they all fit the data equally well, whether it's a finite temperature divergence or a zero temperature divergence. Okay, and answering Pratap's questions, so clearly doing experiments in Fourier space or in wave vector space is not going to answer the problem, but you need to go to real space to see what each theory what microscopic predictions each theory makes. And unfortunately, if you're going to go to real space experiments or simulations, you are stuck here at the bottom 4 orders, which is the least interesting part of the glass physics. So you can't even access the dynamics here, because you can't do either simulations that run too long, or because you can't do experiments that run too long and have access to single particle dynamics. So the question is, how do you distinguish between these competing scenarios? It's not that we don't have enough scenarios that explain the glass problem. In fact, we have too many of them. The trouble is we don't know how to tell them apart. Okay, because you're stuck right here. Okay, and you don't even get, so forget T naught and Tk, you don't even get to Tg, but when you do a computer simulation or when you do a colloid experiment. Okay, so the take that we had a little while ago was that because you have access to single particle dynamics, this curve, although looks pretty boring, there are a lot of interesting things that happen as you start cooling the liquid. Okay, the first thing that happens is the well-known relationship between diffusivity and viscosity, which is called the Stokes-Einstein relation, breaks down at some temperature. Okay, and it breaks down because you have this heterogeneous dynamics. Then we know that there is a theory called as the mode coupling theory, which fails, and we know the reasons why it fails. Okay, and And this is a window. This is a window that we can access both in simulations and in colloid experiments.
Why does this fluctuation distribution theorem break down?
It's not a fluctuation dissipation theorem. It's one instance of it. So it breaks down because you can imagine that you have a dynamical heterogeneity.
Theta becomes heterogeneous.
Yeah, theta is locally heterogeneous because you have a slow relaxing region, you have a fast relaxing region.
Overall it breaks down.
Overall it breaks down because the overall is an average. So let us say that you have a region which is very highly diffusive and a region of very slow diffusivity. So the average will be dominated by the fast diffusion. You do the same thing for the viscosity. You have a region of high viscosity and a low viscosity. The average is dominated by the low viscosity. So D and eta cannot be correlated anymore. Yeah, I'm sorry. Yes, it depends on the length scale. But so all these measurements are done at the first peak of the structure factor, the nearest neighbor length. Okay, so and there are studies as recently as 1 week ago in which people look at the wave vector dependence of the Stokes-Einstein relation. Yes. But then, so all the relaxation times that I measure, for example, the breakdown of Stokes-Einstein are all done at the first nearest neighbor shell. So you have to break at least a cage to get out and relax. So that's the idea. Okay, so the goal was whether you can use colloids to basically, access, even in this small window that's accessible, whether you can distinguish between scenarios, and that's precisely what we wanted to do, okay? Okay, so and the theory that we're going to focus on is called as the random first order theory, okay? So what it tells you is that, put forward by Wallinis and Kirkpatrick and Tumulai about 30 years ago. So what it means is that say you start, with a homogeneous liquid, you cool, you supercool, and at some temperature, which we call TD, okay, it's called a dynamic crossover temperature, the system is going to basically fragment into a whole bunch of mosaics, okay? So these are the different mosaics, and surrounding the mosaics, you have well-defined interfaces. Okay, I'll tell you what's so, why this is so horrendously complicated to go and do this in an experiment, okay? And then what's supposed to happen is that from TD to TK, what's supposed to happen is that the mosaic size is supposed to grow. And this is a static length scale. The theory predicts that the mosaic size grows, and that gives you basically a structural origin for the slowing down of dynamics, okay? So yes, so for about the last 25 years, this is a picture that was motivated from spin glass physics, right?
Coarse graining in magnetic system, I know this roughly spins as same in a mosaic.
So the trouble is this, right? So with this sort of a picture, the trouble is this thing is amorphous. I'm sorry. This thing is amorphous. This thing is amorphous. There is not even a well-defined order parameter to go after. So how do you distinguish between two glasses if you don't know what the order parameter is? And more importantly, identify the interface between them. Okay? So that is the problem with this theory, which is why, but I'll tell you there are ways to get around it. And not in colloid experiments because of the fact that the velocity autocorrelation decays well before the Brownian time, which is not a microscopically accessible information. You can do that in light scattering measurements, but then there you're doing it in Fourier space. You don't have access to real space there anyway, right? And one more thing, if you had a very good microscope in which you could track the particles very well, you'd have to capture truckloads of data just to pull out whether it is, yes.
So S of Q omega from velocity, Fourier transform, velocity correlation functions are not possible.
You see, once I have access to real space coordinates, I can go back and calculate all of these quantities. But I won't be able to show you such an heterogeneous state existing.
Even in velocity correlation.
Yes. Okay. Yeah. Yes. Yes.
So here, mobility-wise, is it like, is it already like liquid state, or is it already caged and trying to form a glass system?
It's a beautiful question. So we're going to exploit that factor to some extent, well, in a slightly different manner. So from going from this state to this state, you already see caging going on. But the theory, the random first order theory really works only after the temperature called TD. No, the caging happens much before. The theory makes no claims about what happens below TD, what happens above TD.
So it's sort of like, I mean, within quotation solidified. I mean, started to solidify. I mean, not exactly free to roam around like this.
Sure. That has happened much before. But the theory makes the specific claim that there are these mosaics, and we don't know what the mosaics are. And it is the growing size of the mosaics that determines tau alpha, or the relaxation time. And we don't even know how to identify the mosaics. Okay, so so they have some sort of a nucleations type argument. Okay, that the mosaics nucleate, so you can associate a surface tension. It should have been d minus 1, but nobody knows what theta is really, because it depends upon the shape of shape of these mosaics. And this is basically the driving force, the configurational entropy. So the mosaic likes to explore various configurations, and that is the driving force. And you can minimize this free energy, find out xi, and interestingly, this expression, this theory gives you the Vogel-Fulcher-Taman relation. Okay, after you minimize, you can assume an activated relaxation, you get this relationship. Okay. Oh, theta is, okay, d is the dimensionality of the space. Theta should have been d minus 1 because it is the surface term, but nobody knows whether it is d minus 1 or d minus something greater than 1. That depends on, that depends on the shape of the mosaics, whether they are compact objects or whether they are fractal-like objects. Yes. So the competition between these two allows you to pull out a length scale, and that length scale is supposed to grow and diverge at tau alpha. That's the claim of the theory. Okay, and it makes a bunch of very unique predictions, which is what's very nice about this theory. It says that there is a well-defined transition temperature to the mosaic state, and it is now we know that this transition happens at close to the mode coupling temperature, and the mode coupling